All right, so welcome to the deep dive.
Yeah.
Today, we're going to be looking at this paper called Spacetime Inertia,
Okay.
a unified energy framework for gravity, dark matter, dark energy, and black holes by
Ugh.
Dave Champagne.
It's a mouthful.
It is. It's quite a paper,
Yeah.
but it's very interesting because it's trying to tie all of these huge concepts in astrophysics together.
Exactly. It's really ambitious, trying to explain all these mysteries with one new framework.
Yeah, like dark matter, dark energy, even black holes.
Right. It's basically saying, what if we've been thinking about gravity all wrong?
Yeah, and I think that's kind of the theme that runs through this paper is that what if gravity isn't a fundamental force, but an emergent property of space-time itself?
That's the big idea, right?
Yeah.
Space-time inertia.
Okay, so let's dig into that a little bit. We're kind of familiar with the idea of inertia, like with objects, right?
Right. Like if you push a bowling ball, it takes some effort to get it moving.
Yeah, it resists the change in motion.
Exactly. It wants to stay at rest or keep moving in a straight line.
So this paper is basically saying that space-time itself has this kind of inertia.
Exactly. And it's this inherent resistance of space-time to any kind of change in its motion or its state.
Okay, so any disturbance is met with this pushback.
Right. And the paper proposes that this pushback, this space-time inertia, might be what we perceive as gravity.
So instead of thinking of gravity as like this force emanating from an object, it's more like the way that space-time is reacting to the object.
Right. Like it's not that things are being pulled together by gravity, but they're being pushed together by the way space-time reacts to energy.
Yeah, that's a really different way of thinking about it.
It is. It's pretty mind-bending.
So how does this concept of space-time inertia help us understand something like dark matter? Because right now we say we need dark matter because we don't see enough visible matter.
Yeah, galaxies are rotating way faster than they should based on the stuff we can see.
Right.
So we say there must be this invisible dark matter providing the extra gravity.
So where does space-time inertia fit into this picture?
Well, what if the extra gravity we observe isn't coming from invisible particles, but from the inherent inertia of the high-energy environments around galaxies?
So you're saying that the energy itself is enough to...
Exactly. Remember, this paper proposes that energy itself can create this space-time distortion, this weight that causes things to move towards each other.
So we don't need to invent this exotic dark matter particle.
Maybe not. Maybe it's just space-time doing its thing, reacting to the energy that's already there.
Okay, so that's dark matter. What about dark energy? That's this mysterious force that's pushing the universe apart.
Right, causing the expansion of the universe to accelerate.
Accelerate, yeah.
And we don't really know what it is.
Right.
So this paper has a really interesting idea about that, too. What if, as the universe expands, this spreading out of energy actually creates a kind of resistance to further expansion due to space-time inertia?
So it's like the universe is resisting being stretched.
Yeah, exactly. Like it's trying to hold itself together against this expansion.
Huh. So instead of two mysterious forces, dark matter and dark energy, we might just have space-time doing its thing.
It's a pretty elegant solution, right?
Yeah, very elegant, like a unified theory of the cosmos. Almost.
It's starting to feel that way.
Okay, so we've talked about dark matter, dark energy.
What about black holes?
Let's talk about black holes. I mean, they're these incredibly dense objects.
Yeah, where gravity is so strong that nothing, not even light, can escape.
Right.
So how does space-time inertia change our understanding of black holes?
Well, I mean, traditionally we think of black holes as singularities, right, where matter collapses.
Yeah, infinite density, a point of no return.
Yeah, but with this idea of space-time inertia, is it possible that...
It makes you wonder, doesn't it? Yeah.
What if a black hole is actually a region of space-time where the energy density is so high that its resistance to change is almost absolute?
So instead of matter collapsing into this point of nothingness, it's more like the energy is so dense that space-time itself is resisting any further change.
Exactly. Nothing can escape because space-time is pushing back so strongly, resisting any more movement or change.
So it's like a cosmic, unmovable object in a way.
That's a great analogy. And because black holes are these extreme environments, they could be the ultimate testing ground for this theory.
Right, because if we can understand how space-time inertia works in a black hole, then we might be able to unlock secrets to how it works.
Everywhere else. Exactly.
So we've got dark matter, dark energy, and now black holes potentially explained by this idea of space-time inertia. It's pretty wild stuff, right?
It's definitely a paradigm shift.
So how do we actually test these ideas?
That's the big question, right? We need to find ways to observe space-time inertia in action. Because right now it's just it's a concept, it's theoretical.
It's a theoretical framework, yeah.
Okay, so what are some of the ways we could actually test to see if this is a fast age?
Well, the paper makes some specific predictions that we can look for.
Okay.
For example, remember how we talked about gravitational lensing? How light bends around massive objects.
Yeah.
If space-time inertia is real, we should see stronger lensing effects in areas where the energy density is high, even if there's no visible matter there.
So we should see light bending more than it should.
Yeah, more than we would expect based on the visible matter alone.
Based on what we could see, yeah.
Exactly.
So if we see that, that could be evidence of space-time inertia at work.
Exactly. It would be like seeing the imprint of space-time itself, its resistance to the energy density.
That's fascinating. So are there any other tests that we could run?
Absolutely. We can look at the rotation curves of galaxies, which is basically how fast stars are orbiting around the galactic center. If space-time inertia is playing a role, we should see stars moving faster than expected based on the visible matter alone, especially in regions of high energy density.
So basically, all these things that we couldn't explain before.
Exactly. The things that led us to dark matter and dark energy in the first place.
Yeah.
Maybe they can all be explained by space-time inertia.
And we've got amazing tools like the James Webb Space Telescope.
Oh, yeah, that's a game changer.
To actually make these observations. And
it's giving us unprecedented views of the universe. And the data we're getting is incredible.
Yeah, so the James Webb is not just taking pretty pictures.
No.
It's helping us to...
It's a powerful tool for testing these theories and pushing the boundaries of our understanding.
To test these fundamental theories about the universe.
Exactly.
That's so cool. This is already making my head spin, but in a good way.
I know, right? It's mind-blowing stuff.
But we've covered a lot of ground already. Before we dive into the nitty-gritty of testing these ideas, let's take a moment to reflect on what this all means for our understanding of the universe and our place in it. We'll be back in a moment to continue our deep dive into the fascinating world of space-time inertia. Welcome back. Before the break, we were talking about how this idea of space-time inertia might actually be able to explain some of the biggest questions we have about the universe, like dark matter and dark energy, and even black holes.
Yeah, it's a pretty radical shift in thinking.
It is. But this paper doesn't stop there.
Oh, no, it goes even deeper.
Yeah, it starts to hint at something even more fundamental.
Yeah, it touches on one of the biggest unsolved problems in physics.
Which is?
How to reconcile general relativity and quantum mechanics.
Right, it's like the holy grail of physics, right?
It is. You've got general relativity, which describes gravity as the curvature of space-time, working perfectly on large scales.
Like planets.
Yeah, planets, stars, galaxies. Yeah. But then you've got quantum mechanics, which governs the world of tiny particles and their bizarre behavior.
Those two just don't seem to get along.
Nope, they're like speaking different languages.
Yeah, so how does this space-time inertia idea potentially bridge that gap?
Well, imagine this. What if space-time itself, this thing we've been talking about, having inertia, isn't actually smooth and continuous like we usually picture it?
Okay.
What if it's actually made up of tiny, discrete chunks? Quantized, as physicists would say.
So you're saying like space-time is pixelated?
Kind of, yeah, like a digital image.
Wow, so the fabric of reality itself might be made up of these tiny little bits.
It's a mind-blowing concept, but it could be the key to connecting gravity to the quantum world.
Okay, I'm following so far. So if space-time is quantized, how does that relate to inertia and gravity?
Well, if space-time is made of these tiny chunks, then its inherent inertia, its resistance to change, could be an emergent property of those chunks, of the quantum nature of space-time itself.
So gravity isn't a separate force, but it's actually a consequence of...
Space-time being. Space-time at its most fundamental level.
Space-time being space-timey. Okay, I kind of like that.
It's the best way I can describe it. But the point is, this could have huge implications.
Yeah, like what?
Well, for starters, it could revolutionize our understanding of time, space, and how the universe evolves.
Okay, now we're getting into some serious sci-fi territory. So we're talking about rewriting the laws of physics as we know them.
Potentially, yes. But of course, this is still a theoretical framework. We need to test it rigorously before we throw out our textbooks.
Right, and that's what makes this paper so interesting. It's not just throwing out wild ideas. It's suggesting ways to actually test them.
Exactly. It provides a roadmap for how to see if this stuff is actually happening.
So let's talk about those tests. Earlier you mentioned that space-time inertia could affect things like gravitational lensing, which is how light bends around massive objects.
Right, like how a galaxy cluster can act as a giant lens, distorting the light from objects behind it.
So how would we use that to prove or disprove this theory?
Well, if space-time inertia is real, we should see stronger lensing effects in areas where the energy density is high, even if there's no visible matter there.
So if we see light bending more than it should, based on the visible matter alone.
That could be a sign of space-time inertia at work, yeah.
And you mentioned another test, looking at the rotation curves of galaxies.
That's right. We can measure how fast stars are orbiting around the center of a galaxy.
Yeah.
And if space-time inertia is playing a role, we should see those stars moving faster than expected based on the visible matter.
Especially in areas where there's lots of energy.
Exactly. High energy density means stronger space-time inertia, which means stronger apparent gravity.
So we're talking about incredibly precise measurements of light and motion across vast distances.
It is a challenging task, but thankfully we have tools like the James Webb Space Telescope.
Oh yeah, the James Webb, that's the one sending back all those stunning images of the universe.
It's not just about pretty pictures, though. The data it's collecting is helping us to test these mind-blowing theories.
So the James Webb is actually giving us the data we need.
It is. It's helping us to see if this space-time inertia idea holds water.
It's amazing to think that we're living in a time where we can actually do this kind of science.
It is an exciting time to be an astrophysicist, that's for sure.
It really makes you appreciate how far we've come in our understanding of the universe.
And how much more there still is to discover.
Absolutely. You know, all this talk about space-time and gravity and quantum mechanics, it's really making me think about something we take for granted every day.
What's that?
Time. So, we're back, and before the break, we're talking about time.
Yeah, time, that ever-elusive concept.
Exactly. I mean, it's something we all experience.
Yeah.
But it's so hard to really define or wrap your head around.
Yeah, it's like we know it's there, but what is it, really?
So does this paper, does it have anything to say about time?
It does, and it's pretty mind-bending stuff.
Okay, I'm intrigued.
So think about everything we've talked about. Space-time, inertia, energy density, warping space-time.
Yeah.
What if the flow of time, the way we experience past, present, and future, is also a consequence of this space-time inertia?
Okay, hold on. You're saying time isn't just this, separate thing ticking away in the background?
Right. What if it's not this absolute universal clock?
Yeah.
What if it emerges from how space-time itself behaves?
So time is like a product of space-time, not a separate dimension.
That's the idea, and it's a pretty radical departure from how we usually think about it.
And that's a big deal, right? Because if time isn't absolute, then everything changes.
Right. It changes how we understand the universe, the relationship between cause and effect, everything.
So how would time work differently under this framework of space-time inertia?
Well, imagine this. Instead of time being a separate dimension, it's more like a measure of how quickly space-time can change in response to energy and events.
So the more energy in a region, the slower time moves.
That's what the paper suggests, yes. The harder it is for space-time to change, the slower time would appear to flow relative to a region with less energy.
Whoa. So time is literally different depending on where you are in the universe.
Theoretically, yes. And that means our usual understanding of cause and effect, where causes always precede their effects, might need some serious rethinking.
Okay, now I'm getting a little dizzy.
Yeah.
But let's bring it back down to Earth for a second.
Okay.
If this is true, does it affect us here?
Well, the effects would be incredibly tiny in our everyday lives. We're talking about differences that would only be noticeable in extremely high-energy environments, like near a black hole.
So no time warps on my morning commute?
Probably not. But on a cosmic scale, these differences could be hugely significant.
So we might not be bending time on Earth.
Right.
But this theory could completely change how we view the universe and its evolution.
Exactly. It opens up so many new questions and possibilities.
Well, you know, that's what I love about science.
Yeah.
It's always challenging our assumptions and making us rethink everything we thought we knew.
It's a constant process of discovery and exploration, and this paper is a great example of that.
Absolutely. And you know, what's even more exciting is that we're living in a time when we have the tools to actually test these ideas.
We have telescopes like the James Webb that are giving us unprecedented views of the universe.
And who knows what we'll discover next.
That's the beauty of it. The universe is full of mysteries, just waiting to be uncovered.
Well said. And on that note, I think it's time for us to wrap up this deep dive.
Yeah, it's been quite a journey.
It has. We've gone from questioning the nature of gravity to rethinking the very flow of time.
And hopefully we've sparked some curiosity and wonder in our listeners.
I hope so, too.
Yeah.
So to everyone listening, keep questioning, keep exploring, and never stop being amazed by the universe.
Because there's always more to learn and discover out there.
Thanks for joining us on The Deep Dive.